in any case, let us then start. Are we already streaming on Suresh?
Yes, we are.
Oh,
Yes, we are.
all right, good. Welcome, everyone. It's actually a great pleasure to have this extraordinary, I must say, panel discussion at the end of a week-long meeting on the dual mystery of gauge theory and gravity conference, which saw a galaxy of speakers. And we are seeing actually a subset of them here, and really eminent people. The leading panelist is Professor David Gross, a very well-known theoretical physicist and a pioneer in the field of string theory, and also a galaxy of panelists. And as the lead panelist, Professor David Gross has kindly agreed to also introduce them in turn. And this discussion is, related to a very important question of interaction between fundamental science, especially fundamental physics, as we are practitioners of it, and society at large. And so this is really a very important, topic which we must all think about as both members of society and of science. And therefore, I'm really pleased and welcome all the panelists and attendees on behalf of the Department of Physics, IIT Madras, and the organizers of this meeting, Professor Suresh Govindarajan and Zayan Mukhopadhyay. So I just have some, guidelines as to how we will conduct ourselves over the next few hours, and I'm addressing myself primarily to the attendees. So the rules of the game are the following.
Yes, hello.
First, Professor David Gross will take over, and he would actually, conduct the. He would be the master of ceremonies, so to speak, and there will be a discussion in the panel and back and forth within the panel. And at the end of this, Professor David Gross will indicate us when we should step in and take part in the larger discussion. So I would request all of you to please keep your questions till the end. You may write down your questions in the chat box, and please identify yourself, especially if you're outside of the IIT Madras system, so that we can look at your question. And please keep the question to the. This is very important. I can't overemphasize this. Keep it to the topic of the discussion, okay, which is fundamental physics and society. So we would look at your questions, and of course, if it's possible, we would have you ask the question and interact with the panelists, especially if there is sufficient time and the question is of relevance to this particular panel discussion. So please keep the questions sharp, short, and interesting, and please listen in carefully. And I'm sure we will have a very invigorating panel discussion that we should that will make us think in the future and probably even determine the ways we act. So I'm really hopeful for it, and I'm really happy that the panelists have come in here, and we really look forward to it. So let me then invite Professor David Gross to take over.
Can I have 2 words before that? Can I have 2 words before that, David? Yes, I just wanted to say that Mani is probably able to join us soon. He's now just entering the panelist password. So the only issue could be that we have some problem at that somehow the system doesn't allow him to log on. I don't know why, but I think he has sorted everything out. He has been able to download it, and he's just trying to get it. I just want to say a few words before this thing. So,
can you? Spenta is sharing his screen.
Yes, can I please request?
Please stop.
Professor Spenta, can you please stop sharing your screen? Or panelists on the screen together with the videos on. Thanks. Okay, David, I just take your permission to say a very few words before we start. So I just wanted to say that today we are facing a threat to free speech all over the world, and this culture of debate and discussion are essential for the progress of human society. And this is seemingly being replaced by very fake propaganda and polarization of opinion. We are not talking to each other anymore. And social media is also not doing enough to bring us together. But India has been one of the countries in the world where from very ancient times, particularly from 3rd century BC, the culture of debate and discussion has flourished ever since Ashoka held one of the greatest Buddhist council, the 3rd Buddhist council, where all matters of spiritual and civic life were discussed, and there were even rules formalized that you cannot extol yourself when you present your own opinion, and you should always treat your opponent with mutual respect, and do not unnecessarily offend people, practice moderation and all this. And this tradition has been carried all the way to Akbar, the great Mughal emperor, where he even invited atheists along with all religious leaders to come and debate and discuss. And physicists play a very important role in the modern world because they're entrusted with finding the secrets of the universe, and they give a meaning to our collective human existence today. And if Buddha would have been alive, he would certainly said that this quest for collective truth and collective search for happiness is the most important goal of human society, and this is above personal enlightenment, because his enlightenment was never personal. It's something that brought about a social revolution in India, that the search for knowledge based on equal democratic participation is the highest goal of humanity today. And science today embodies this vision. And beginning from Albert Einstein, many eminent physicists have done a great job in upholding social values in moments of great crisis in human history. And they have not only unraveled mysteries of the cosmos, they have also done a great job in upholding these great human values. And sometimes physicists have failed, but from Albert Einstein to Lise Meitner to Edward Wheaton and David Gross, we do have a gigantic legacy today. And in this context, we should also mention Meghnad Shah, of course. Today, theoretical physicists has progressed a lot since the beginning of the previous century. We have learned about our origins, cosmic origins, fundamental laws. In the new millennium, we have verified many important theoretical predictions of the last century. And these are the Higgs boson, which gives mass to all fundamental particles. We have found the gravitational waves from colliding black holes, and we also have seen the ripples in the cosmic microwave background radiation, which gives rise to the structure of the universe today. And all of these have required a lot of patience from society, and also billions of dollars of funding and very intense international collaboration. But most importantly, it has tested, right, the fundamental values of society, without which these fundamental discoveries would not have been possible, because this has required decades of groundwork and patience. However, these experiments have also told us that how much vastly we don't know. And to unravel the mysteries of the universe today, we have to do a lot of speculation that might seem very abstract and very naive and very absurd even, because even 100 years ago, when gravitational waves were first proposed, it was not even clear if we will be able to measure them by measuring shifts in distances that are about 1,000th of the radius of a proton. But even it was not clear even to Albert Einstein whether gravitational waves are real in the first place. And today we face a very similar situation, because and this is the main topic of panel discussion, which will be basically two questions. One is, how and why should society support the quest for fundamental laws, which will take about a century to become a collective and concrete truth? Why should society be patient for 100 years for a concrete truth or concrete collective truth to materialize, and what society gains by that? And secondly, how should researchers in fundamental physics will uphold the values of society, uphold human values, and not only produce great research, but also do it in the right way, and also communicate it back to the public in the right way? So these are the two major questions. And of course, there is no one better than David Gross to lead such a discussion, because he's not just a Nobel laureate in physics. It's too little to say that he's a Nobel laureate in physics. Physicist. Something very tell about a physicist. And he has not only shown that nuclear physics can be described by quantum field theory, or this something called the gauge theory of color force, quantum chromodynamics. He has also found one of the 5 consistent quantum gravities, one of the string theories. He has co-created one of these, and he has been enormously influential among theoretical physics. He has helped India and China build a lot of this infrastructure for theoretical physics. And not only that, he has been a proponent of the Humanist Manifesto. So he's the physicist and the right person to chair such a discussion today. So we are very happy that we are able to record it for posterity. So over to David now, and we will be very thrilled to see what we hear today.
Thank you, Ayan. It really is a pleasure to be here in this discussion, panel discussion with so many of my friends from India and from elsewhere. This has been an incredible week. You know, I was supposed to come to IIT Madras and give the convocation address, which I will give on Sunday, although it was recorded. But the COVID intervened, and my friends in Chennai at IIT Madras decided to go ahead anyway and organize a conference on string theory and quantum field theory and exciting theoretical physics. And they put together a wonderful meeting, which I have tried to listen to many of the talks. So they all occur either early in the morning, very early in the morning, or very late at night, much like this panel discussion is occurring. Introduction, Suresh and Tanay, for putting together such a great conference. Most of the panelists gave lectures at this conference, really great lectures. I think they're all still available, the lectures, if you want to listen to them on the web or at the IIT website. But then they also had the idea of having this sort of panel discussion among us, addressing a wider audience and dealing with some of the sociological and cultural issues having to do with the frontiers of theoretical physics and society. And that was a great idea. They also put together a marvelous set of questions and topics that we might address. And I'm sure all the participants in the panel have looked at those questions and probably have additional issues they would like to bring up. So what we're going to do is have each of the panelists give a short of the order of 10-minute presentation dealing either with the questions that were posed or whatever else they want to speak on these various subjects. And after that, we'll have questions from the panel and discussion. And at the end of everyone talking, we'll open it up to the streaming audience for questions and discussion. These are difficult times. We're all living in extremely difficult times due to the COVID plague, which does not seem to end. Goes on and on and on. And yet, in the midst of all of this, at least our community, and I think many other communities as well, have discovered new ways of connecting and talking and exchanging ideas and interacting. Certainly in the field of theoretical physics, there have been more talks and lectures and conferences like this one than ever before, and more available to the world as a whole than ever before. I mean, it's quite remarkable that we're able to carry out this kind of meeting with people all over the world. And this is something I think is going to persist after the COVID disappears. It's wonderful for the developing world because we're all equal in this virtual, multiply connected universe. And it's very good for science because it overcomes a lot of the barriers between countries and peoples that unfortunately appear to be increasing as opposed to be decreasing. But through Zoom and WebEx or whatever this is, Cisco Web, we can overcome these barriers put up by ignorant politicians. So I'm not going to, I will intervene during the discussions, but I'm going to leave it to my friends, my many friends here to directly address some of the questions. And I'm going to start with a friend of physics, a friend of mine and a friend of India, Mani Bhaumik. Now, Mani Bhaumik is not a string theorist, although he loves string theory. And he is, however, a physicist. In fact, he's the first PhD that ever got his PhD from an Indian Institute of Technology back in 1958 from IIT Kharagpur. He was a student of Bose. And the States, where he worked in industry and is famous for the discovery and the development of the excimer laser, which is so important in designing chips and also in LASIK surgery. But he always retained his love and admiration for physics, and in recent years, he has been extremely generous with his fortune and has been helping physicists and physics institutions around the world, including India and in the United States, where at UCLA he helped fund the Mani Bhaumik Institute at the Department of Physics at the University of California, Los Angeles. So Mani brings a different perspective to this group. He's a friend of physics and an observer of developments in physics, and he's a perfect position to address why physics should be of interest to the wider society and culture. Mani.
Can you hear me?
The floor is yours.
Thank you. Can you hear me?
We can hear you very well.
Okay. Thank you, David, for the wonderful introduction. And good morning to everybody. I really am delighted, not only because I'm invited to this wonderful panel discussion, which I could not even think of in my early days, as David mentioned, in 1958 at IIT Kharagpur. It has come a long way. And so it's so nice to see that ION has been able to organize such a wonderful panel discussion. And more so for me, I really think that you have done I couldn't have done a better job than choosing anybody than David Gross to moderate this meeting, because David is not only a highly respected outstanding scientists who developed as you know, the Nobel Prize winning subject of asymptotic freedom that led to the QCD. But he is a genuine the interested person in the development of India for a long time. And in fact, I see quite a few students of his in the panel who would be talking later on. But I'd like to say that what David likes to talk consistently is that we should not make in India, develop, make in India. And wonderful, very wise statement. And I think that in every developed country, this is something that is done, that either develop the technology or transfer the technology somehow, and then build it. And I think IIT in a very good position to really accomplish that development part, because I think a good, perfect example is Narayan Murthy, who is a graduate of IIT, Kanpur IBS, and then he started this fabulous Infosys that has really has been remarkable throughout the world, almost well known. And but I'm sure that this is only one example, but I think David's siren song that develop and make in India is something we should really take it into heart. And IIT is really in a good position to do that. Now, as you know, IIT was Nehru, the first Prime Minister of India, Nehru's dream child, and he wanted to actually modulate after MIT of USA. And I guess one have to say that it has been really successful to a large extent, but only in the undergraduate area. And this has been remarkably demonstrated by the famous TV anchor, Leslie Stahl, in CBS 60-minute section, not only way past, but only a few years ago. And so in that sense, Nehru's dream of IIT being the MIT of India has come a long way. But there is one big problem that I see, that it has only been in the undergraduate area. There is a substantial problem or deficiency in the graduate or postgraduate area. I know that India is aware of it, and that's why they have appointed some committees like the Kakhotkar committee. And I understand that following that, there has been some substantial increase in the amount of money in research, as well as for the salaries of the research students, which is essential for them to follow. But somehow it has not really gelled yet. I don't know exactly why, because I've been out of India for about 6 decades. But one thing that seems obvious, that to really catch up to the situation fast, we have to transfer the technology. And what better way to than to invite the visiting expatriates from USA and elsewhere to come and try to transfer the technology in a fast way. Now, some of it is being done, like some people have gone to Mumbai, but I think Mumbai IIT, I mean, but I think more needs to be done, and that is something that can be facilitated by the extra money that the departments or the IITs have received. The other area, the most important to me that I see is necessary and which is exemplified by this wonderful panel discussion that ION has organized, is that there has to be a good mix of fundamental science with technology. I don't know exactly why, but there is a definite synergy there that is really necessary. Look at MIT. Right now, there are about 8 Nobel laureates actually in the physics department out of 100 over the years as a whole. And also same thing is in Caltech, California Institute of Technology here in Los Angeles, where it is more known for Nobel laureates in physics than in technology. And yet, of course, they have produced giants like the Intel inventor and other technological experts. But there seems to be really it's a necessity that these kind of not only panel discussion to increase the sensitivity or the need of it to the public in general, but also this is something that is a proven fact. And this is why, as you know, MIT as well as California Caltech are in the top tier of the London Times survey of the best universities in the world. And unfortunately, IIT has not made it there yet. And hopefully, this kind of stimulus that will be given by these joint cooperation and also emphasizing the need for the infusion of the ideas of the physicist into the technology would be very helpful. And I thank you, Ian, and all the other people who has been involved in that. And I think my time is up, David. Is that right? 10 minutes?
Yeah, that was great. So you brought up one of the issues that the organizers suggested that we talk about, which is the relationship between sort of basic science, highly theoretical science, and technology. And the fact that the IITs haven't emphasized enough of advanced research. I mean, maybe Sunil could talk because he is one of the leaders at the ICERs, which were set up to do exactly that, to mimic the IITs, but to do more basic science and research. Sunil, do you want to add something to?
Sure, I'll be happy to add something. So, a couple of things I can add to what Dr. Bhaumik just said. Now, one is that the quality. I should first step in a little bit to defend the IITs. The quality of research there in all fields, both pure and applied, has ramped up dramatically in the last decade or 15 years, in my opinion, and that's a very good sign. The other thing is that there are now 7 ICERs which don't have technology, but which do have undergraduate teaching and fundamental research. And, if you look at the outcomes, we are not CIFR, we are not IISc Bangalore, but we are certainly getting to a point, all the ICERs have kind of declared that, fundamental research is very, very important. You're not going to get a job or a promotion just for teaching well, though you have to teach well. It's really, this has been asked 100 times of us, is it enough to teach? Is it enough to do research? The answer is no to each of them separately. You have to do both. We have benefited from great funding for a while. I'm sorry to say that's not the case in recent times. But we have a diversity of research interests all the way from string theory and gravity to experimental high energy physics, superconductivity. Now we've started data science, Of course, we have a fantastic biology department, a chemistry department. So I think it's all in the right direction. I'll be happy to answer any specific questions.
Yeah, I'm sure we all agree on the point that Mani was trying to make about the importance of basic science, which is one of the questions that the organizers put to us, namely, why should for example, a technical institution like IIT support and encourage theoretical research in quantum gravity and string theory? And should there be a separate center for such theoretical research, and what benefits can institutions like IIT Madras get by supporting fundamental research? I think we're all in agreement, but this is a question that arises everywhere in the world, really. Most of us are engaged in highly speculative, highly theoretical research at the frontiers of physics, which indeed are bound to lead to technological and innovations and benefits for society, but over a very long range of time. And it's often a question that's asked in developing countries, which aren't have scarce resources and many problems. Why should we spend money on such things as opposed to more practical problems? Mani quoted one of my statements a few years ago when I was visiting India and hearing Prime Minister Modi slogan, "Make in India." And I said, it shouldn't be "Make in India," because if you just make in India, you'll be making stuff invented somewhere else, finding it very hard to compete with the rest of the world. And I suggested that a better slogan would be discover and invent and then make in India. And that is a lesson that the Chinese have learned very well. And it is, I think, really essential. Unless you are world-class in basic science, you'll always be using other people's ideas and they will have an advantage. And India certainly has the capability to both discover and invent and then make. And even in fields like theoretical physics of the type that we engage in, string theory and quantum gravity, although it is not possible for us to make the argument that our studies will lead to immediate applications. That's extremely unlikely. However, unless you have a strong basis in the most exciting areas of frontier science, you will not be able to have a thriving, healthy basic science infrastructure that eventually leads to new innovations and new technology. And that's because you, number one, will lose the best people. Often the brightest young minds want to tackle the most interesting and difficult problems at the frontiers of science. And if they're not able to do so in their own country, they'll go elsewhere where they will be able to do that. And second, even if the road from these fundamental discoveries to to applications is long, the indirect influence of discoveries in the basic sciences is enormously important for all the other areas, more applied areas of science that directly connect to technology and to economic development. There are so many examples of this. I don't have time to discuss it, but believe me, it's true. I think we'll go on now to second speaker, who happens to be one of my first grandchildren, and that's Kumun Vafa, who is one of Ed Witten's first students. Ed Witten was my first students, so he's probably my oldest grandchild. Kumun is a very distinguished string theorist and theoretical physicist who made enormous contributions to string theory. Most famously, perhaps, is his demonstration with Andy Strominger that string theory can account for the entropy of black holes. This is really a seminal contribution which convinced everyone, they needed convincing, that black holes could be understood within string theory. This gave an enormous boost to string theory, of course, but also solved a problem that had been around ever since Bekenstein and Hawking argued that black holes had an entropy, dynamic entropy. And Kumun has done many, many things from F theory, and now is the leading explorer of what's called the swampland, those areas of those potential theories of gravity and of elementary particles, which cannot be in string theory. He's mapping out areas which are where we shouldn't go, but that places constraints on what we can do, but it also, in a sense, raises challenges, tests of string theory, because if we were able to find experimentally signs that we are in the swampland, then that would be strong evidence to disprove string theory. And every theory, even string theory, needs to challenge itself by making predictions that can disprove the theory. Kumun, by the way, is also the author of a marvelous book, which he sent me.
David, thank you.
I'd like to recommend to all of you. It's called Puzzles to Unravel the Universe. And for those viewers who are not experts in quantum gravity or abstract mathematics, this is a great introduction in a way that is very, very enjoyable. So I don't know how you buy this book. I don't think Kumun can send it to all of us. But maybe he can tell you where you can get it. It really is a great, great book. Kumun.
Thank you. Thank you so much, David, for such a generous introduction and kind introduction. It's an honor to be your academic grandson, I guess, it's the terminology. So it's also a great pleasure to be part of this distinguished panel and on a distinguished topic as part of this wonderful conference. I will try to share my screen, and I hope it doesn't cause confusion. Let me try. If it's going to be there, it will be probably best, but I will start the discussion. So yes, so I think you can see my screen share. I hope.
Yeah.
Yes.
Perfect.
Thank you. So I will start with basically asking some of the basic questions that we had described. Of course, human curiosity knows no boundaries. We do not have a good answer as to why. Whether one is a scientist or not, one is driven to look for answers to fundamental questions. For example, where do we come from? What do we know about our universe? Why are things the way they are? What is in store for us? You know, these are all common questions, and it's hard to believe answers to these questions will affect our living conditions in the short term. Nevertheless, we still look for answers. And this is the kind of questions that not only scientists make, but also ordinary people make. It's nothing particular to scientists. It's so basic. So, in fact, for many scientists, the most beautiful aspect of physics are not the complicated math equations or even the ability of predicting how things will happen. What attracts us to physics is what it teaches us about the bigger picture. The general philosophical lessons that are embedded in physical laws are what excite us. For example, the fact that all particles and forces get unified within string theory teaches us about the philosophical idea of unity underlying our universe. The amazingly vast collection of solutions to equations of string theory suggests that there may be many universes besides ours, the so-called vast string landscape. Or what happened before the Big Bang? Or was there a time before the Big Bang? Well, the duality symmetries in string theory, which exchanges small spaces with large spaces, this amazingly unintuitive symmetry, suggests that perhaps as we go back in time, the universe was effectively getting bigger instead of smaller. This suggests we may come from other universes. Physics teaches us deep facts about our universe and our place in it. Scientists and string theorists in particular hope they can add a little to this beautiful story. These questions and their answers are clearly of interest, not only to string theorists, but also to general public. Trying to measure impacts that deeper understanding of these questions will bring about in monetary terms would be a mistake, in my opinion, as the motivation for answering these questions is not driven by economic factors. It is deeper than that. However, even though economy is not the main aim, history provides side benefits. For example, the World Wide Web was a direct outcome of efforts of experimentalists at CERN trying to perform experiments at highest energies possible to unravel the laws of the universe. So even though economic factors should not be the reason society supports science, whenever a human mind is focused on deep and important questions, there typically are good side effects. Now, one may also ask whether support for research in fundamental science should only take place in rich countries, which have the luxury to direct resources in such directions. However, again, history points to the fact that science is a timeless and borderless adventure. A beautiful example of this is Ramanujan. You know, his talent had no boundaries. In fact, you know, he started teaching himself all the things that he amazingly contributed to in the context of mathematics. But in fact, his contribution went beyond mathematics, and it was timeless. What he did at the beginning of the 20th century with his work and also with others, including Hardy, ended up being one of the cornerstones of what we used in the context of what David mentioned, in the context of black hole entropy, in the context of string theory, which came up towards the end of the 20th century. Starting from mathematics all the way to physics of black holes, has no particular boundaries here. Being Indian, myself being Iranian, Hawking being British, Andy Strominger being American, all the rest of string theorists from all over the world, there is no boundary, there's no border, neither in time nor in the subject, and nor in geography. Another beautiful example of this, which also emphasizes, in addition, the genderless aspect of science, is the famed Iranian-American field medalist, the late Maryam Mirzakhani, and she proved that, again, the science is borderless. Let me mention again that, as was mentioned, string theory is a prime candidate for a fundamental theory of nature Not only it unifies all the fundamental forces and particles into one framework, but it also unifies many purely mathematical ideas. It is, in a sense, a unification of mathematics with physics. It is being pursued across the globe, and it's fair to say that many important contributions to this continually evolving field has taken place from scientists from all over the world, and in particular from here in India. It is thus very natural to continue to cultivate and expand supporting research in this fundamental field here in India and across the globe. Now, one may be worried about the fact that research in string theory is a long-term proposition. So why should we spend our resources on it when we cannot see its benefit in our generation? And for this, I thought perhaps I will recount the story which has been put to poetry by a beautiful poem by Malik al-Shu'ara Bahar, the Persian poet, which narrates the story of the Sassanid king Anushirvan about 2,000 years ago, where in the poem it goes to say that as he was passing by a farm, he sees a 90-year-old farmer planting seeds of a tree. And he looks at him with astonishment. He says, "What are you doing? What are you doing here? You're not going to get the benefit of this tree, the fruits of this tree. What are you doing this for?" And he said the following poem in the answer to the king: "دیگران کاشتند و ما خوردیم، ما بکاریم و دیگران بخورند." The generation before us planted the trees and we bear the fruits of it. It is our duty to plant so that the future generations benefit. Thank you. Except I don't know how to unshare. Thanks.
Where am I? Okay. Thanks, Kumran. Is there anyone who would like to add to Kumran's defense of string theory?
Well, I guess we will be doing it in our presentations, hopefully.
Okay, that was beautiful. And our next speaker is Sandeep Trivedi. Sandeep, who is now the director of the premier Physics Institute in India, the Tata Institute, is also a very eminent string theorist who has contributed much to our understanding of string theory. Perhaps he's most well known for being the T of KKLT and proposing a string model that might describe our universe. Our universe is expanding due to what appears to be a cosmological constant, or sometimes called the vacuum energy or dark energy. It's really negative pressure, but anyway. But the universe is expanding rapidly, and that's very hard to accommodate within string theory. In fact, on this very panel, we have two guys who could carry out a very interesting discussion, the type of which we theorists do all the time. Kumran might argue that the de Sitter space that we seem to observe experimentally it cannot be accommodated within string theory. Whereas Sandeep is one of the authors of a proposal to do exactly that. But we're not going to get into a fight here. rather let Sandeep talk about whatever he wants to talk about, some of the issues that proposed. Sandeep, please.
Thank you. Thank you so much, David. I do want to say to David and everyone that, in fact, my term as the director of TIFR ended about a week ago. So I'm not currently wearing that hat anymore. But I do want to start by felicitating David and thanking him. Of course, his role as one of the preeminent scientists of our times has already been highlighted. But I want to acknowledge especially his role as a scientific leader, specifically for India, the invaluable help, David, you've given us in shaping science and the growth of science in our country. And I especially want to acknowledge that role today for the Tata Institute of Fundamental Research, both in the founding of the International Center for Theoretical Sciences and its subsequent growth, and more generally, the invaluable advice and guidance I received from you for the Tata Institute as a whole during the past 5.5 years. So really, thank you very much, David, for all of that. And I think David is muted. He has muted himself, but anyway, thank you.
I just wanted to say congratulations on becoming.
Thank you. Yeah, it's a big relief. I also want to thank the organizers for the opportunity to be on this distinguished panel. I have a few remarks which I've prepared, keeping in mind the questions you all had thoughtfully prepared and sent us. But before I start, please don't mind raising the following issue, and I awoke to it only yesterday, so it's really my fault as well. But the whole panel is very distinguished, but consists of men. And I did think I would bring that up. It would be nice to have more diversity in panel. I'm sure we'll all agree that we'll be successful in unraveling the mysteries of humanity if the remaining half of humanity is also part of our discussions on how to go forward. So I hope we can keep that in mind. But anyway, it's a great honor to be here, and thank you. Now, what I did was I prepared some remarks. Many of them have already been mentioned by Kumrun in his beautiful comments and by Dr. Mani Bhaumik, but I'll quickly run through them, sort of for continuity, and then come to some India-specific remarks, which maybe might not have been made so far, at least. Quantum gravity, particle physics, and cosmology, as has been said already more than a few times here, seek to answer some of the deepest questions about nature. What are the fundamental laws that govern its workings? How did the universe begin? What is it made up of today? How will it end? These are questions which have fascinated humankind from the dawn of time. We already have echoes of this from very early on in the hymns that were composed. But what is remarkable today is the opportunity we have of bringing the full power of scientific thought, grounded logic and precise mathematics, and shored up with hard experimental facts to answer some of these questions. This is really remarkable. This is without parallel in history. And we really must make the most of this opportunity and continue to go forward in this important quest for humankind. Now, I didn't mention string theory explicitly so far because I really view it as part of this broader, grander, so to say, enterprise. But let me do so. Somehow the whole panel is also made up of string theorists. I don't know whether this was by design or anyway happened. But let me say a few things. I think string theory is today and will remain for quite some time to come, in my view, probably a theoretical endeavor. This doesn't take away from its great promise, its great beauty, and its power. It should be said, has been learned from the theory already, even though it has been a theoretical enterprise, because of the compelling logic and the the consistency, and the connection with mathematics the subject has, which allows us to make great progress. When I entered the field, for example, we did not know whether there was a consistent quantum theory of gravity that could be formulated at all. This was a big question. Today, even though we may not have a rigorous proof that might satisfy, say, mathematicians, most practitioners would agree that there is very good evidence that in some situations, anti-de Sitter space of the kind which arises in string theory, there are consistent quantum theories of gravity. This itself is a great advance in studying the fundamental questions tied to nature, tied to gravity. And it's a question whose significance and the progress we have made in answering it, I think, can be conveyed to the public. I usually find the public receptive to the quest, the important quest we are engaged in. They may not quite understand the Baroque details, nor is that so important. But I think bringing about a shared understanding of the importance of the questions is not so difficult and possible to do. And when it comes to such advances, I've found in my own experience that, at least I believe so, that one can get it across to the public. So there have been important advances in the subject. I think the logic, the mathematics, and the rigor of the subject is such that these will continue to happen. And they will continue to be as remarkable as this progress I mentioned. You know, the understanding of what we've learned in gravity, for gravity in anti-de Sitter space, the non-perturbative formulation is so counterintuitive, so remarkable. It's akin to the kind of breakthrough we had, I would say, when we formulated quantum mechanics. It's a completely different way of formulating gravity than one might have thought at first, in one lower dimension as a gauge theory. And of course, the practitioners have grown to accept it. But the fact that we have achieved that progress over a decade or so is actually, if you step back, I think, really quite remarkable. So I think we can look forward to progress like this. And I think we can convey the importance, as well as the fact that the progress is happening, to the public at large. Okay, I want to say one more thing about the subject, and then I'll move on from string theory, which is, I think the standards of the field are extremely high. There's a great deal of collegiality, but there's a great adherence to strict logical thought and mathematical rigor, and we cannot sacrifice that as we go forward. We want to connect with experiment and so on, but you know, that anxiety, if I may say, cannot get the better of us. The subject has a certain course of development grounded in its own logic, and we must listen to it and develop it. Okay, and I think we have to adhere to that standard of rigor, because without experimental support, if we abandon that rigor, we are nowhere. We have no anchor left. And so I think we must do that. At the same time, it's not mathematics. And I think one of the great things about our community, I feel, is that we collectively can strike just the right balance. We collectively have a good judgment of how much rigor and consistency of thought is needed, and no more. And therefore, because of the high standards of the community and the nature of the subject, its great depth, I feel that we are in good hands. We are going to make very good progress in the days to come. So this is what I feel basically about the subject. Now let's talk about experiment and the engagement with society a little bit. You know, as I said, I think the theoretical end of this grand endeavor of seeking the fundamental laws will, of course, remain for some time to come, I think, theoretical. There will be spin-offs, the connections that were achieved between conformal field theory and John Simon's theory and condensed matter physics is an example. There'll always be connections because all knowledge is connected, but that is not our primary motivation, nor should we try to convey to the public that is our main motivation. That's disingenuous. That doesn't serve any purpose. We have to do our communication with honesty, but at the same time, of course, bring out the fact which people know. The people, especially in India, have an intuitive understanding that the deep truths of nature and of all of human knowledge are in the end connected. And so I think that point can be brought across without overdoing it. And it's important to say it, but with the right perspective. Of course, there can be serendipitous, great unexpected discoveries. We might find that there is a stochastic gravitational background filling the universe, which comes to us from very early in the history of the universe, which is the most sensitive probe to high energy physics we can ever. This could happen, and it would be great. We're not banking on it for making progress with what we have in our hands in string theory, but it could happen. So we are open to that. And if some of that happens, so much the better, and we'll make the most of it. And we have to try and do those kinds of experiments. But, we are going to go forward anyways. It is important, though, I feel, when we connect to society in our public talks, that we couch what we do within the larger perspective of the grand endeavor. To show a snapshot of the cosmic wave microwave background and convey that, in fact, this is a photograph, more or less, most probably, of quantum fluctuations in the fabric of space-time so early in the history of the universe that we can actually film this photograph, show it to people. What can be grander than this? And I find, at least, of course, I'm in the field, but I find it takes the breath away when you convey it. People respond to that. As Kumrun said, they're interested in the deeper questions, the philosophical questions, that science has this power. I think if we bring it across, they're going to respond. So there might be experiments which connect well and good, and we have to be open to them, and we have to do it. Now, I want to say one more thing. It could be that in the course of our development of these subjects, we realize that there are fundamental limits on human knowledge. These might arise, for example, because we are ultimately applying the laws of quantum mechanics to our world, or only the corner of the world we have access to. If it can be firmly established, it's far from clear today. If it can be firmly established that there are such limits to human knowledge, that itself is great progress in our understanding of the fundamental laws. We have to see whether it's true, but we should be open to it. And it's not necessarily a finding thing. To understand the limits of knowledge is maybe something we come to in the course of pursuing it. Okay, I just mentioned that thought, but let me only say it and go ahead. Now, of course, in the widest perspective of particle physics and cosmology, there are going to be important experiments that happen, and we have to talk about the participation of India and the developing world in them. And I'm going to say something about it. I think I might be a little out of time, but I just seek 2 minutes more, David, from you on that. I'll say one more thing about science communication, or communicating about science here. And from now on, I'm going to slightly don the administrative hat I had until recently to draw on my experiences. Okay, I think conveying to the public is one thing, but conveying to funding agencies the importance of science is another, as many of you have brought up. This is not so important for theoretical sciences. The amounts of money involved are small. In India, there isn't a shortage of faculty positions. This is a remarkable thing, because we are seeing what's perhaps the second great wave of the expansion of educational opportunities and institutions in the country, with warts and wrinkles. That's going to continue, because the government and everyone knows you cannot sustain a growing economy of 5 to 8% without a growth in educational opportunities. So that's going to happen. There are going to be jobs, and jobs are primarily what you need as a theoretical physicist, along with the internet, which we have. But for experiment, it's an important issue, because the experiments in our area are mega experiments, international collaborations requiring large chunks of money. Now here, my experience with New Delhi, at least, was that in fact, it is not hard to make a case in principle for the funding, even for large science projects, okay, of the order of $100 million US, $200 million US. And I can count for you, I'm not going to do it, projects of this magnitude that the government has in principle agreed to for India to participate in, even in the past 5 years that I was director of TIAFA. So in principle, there is a considerable receptivity in the government for India doing big things, adventurous things, and so on. Now, actually executing it on the ground, okay, ensuring the budgetary flows, these are other matters, but they're extremely important. They are connected to having a good process of advocacy within the scientific community, a good engagement with the public, which can keep up the pressure. Here, scientists do, in India at least, very poorly. I'm going to flag one example because most of the audience is in Chennai, and this example pertains to what I think is the most important big science experiment in particle physics India is going to be involved in. And I know all about it because the Tata Institute is the lead organization, and this is the Indian Neutrino Observatory. It's a great experiment. We have an edge. There's a detector technology, TIFR and related institutions built up, unique in the world. We have an edge for doing great science. We got the government to commit to $200 million, and the project is a non-starter. Why is it a non-starter? Because we could not convince the public that neutrinos, we are not even going to produce no neutrinos here. Simply the neutrinos streaming through the atmosphere, reaching us anyway, are not going to do any harm just because we set up a underground detector, deep underground, to measure them. We couldn't convince them. And, you know, it's people in Chennai have worked extraordinarily hard. So if anything, it's the failure of people like me who were in the kind of positions I was in. But it's a shocking failure. And what it illustrates, and I bring it out here, is, for me, is the poor connect between us scientists and our ability to convey the importance of large projects of this type for India and for science and the growth of the country. So in these kinds of matters, we need to do much better. Our academies of science in India are viewed very poorly in New Delhi today. Now, you can argue about this, but the fact of the matter is that the government of the day in a democracy represents the popular will of the people. We have to humbly engage with them and convince them in terms they will understand. We don't do that. There is a terrible reputation that the academies have, because of which there's very poor advocacy. These are extremely important points when it comes to engaging with society, I feel, for scientists in India. Okay, I'll say two more things and end. Mega science projects, the problem is this. There are many projects and India is committed to them, but there is no systematic analysis of how does India get the best scientific bang for its limited bucks. Okay, are we going to take part in CERN as an associate member, the Indian Neutrino Observatory, LIGO, the TMT, the Square Kilometer Array, the ITER project, and so on and so forth? If you total up all the in-principle commitments India has made, it's unsustainable. It's unsustainable, especially, and this brings me to the last point, because the denominator of how many scientists there actually are in India who can effectively participate in that science is small, is very small, all too small for that kind of money. So if we are going to actually have effective support from the public in the long run for such involvement, we have to grow the scientific base of our country. And that's why the IITs are so important, and the ICERs are so important, and the universities are so important. And here I think we are at a very interesting juncture because there's a new national education policy. Some of you in the panel have worked very hard on it. You'll, I'm sure, say your thoughts on it. There's a new national policy in India. There's going to be a new National Research Foundation. But connecting that education policy to the growth of our scientific community in our universities and research organizations is absolutely critical. We have to engage in it. All scientists have to engage in it, especially in research institutions like mine, if we are going to be successful about it. So I've said a lot, I apologize. But I think to the young people of IIT listening, I'll say this: it's a great future to be doing science in India. The economy is growing, there are jobs in academia, okay, and there's a growth of Indian industry. There's no time like this to use the power of science to transform India. There are plenty of good paying jobs. Convince your parents, don't become an engineer. I'll say this to IITians, don't become an engineer, do science, change society and advance human knowledge. Thank you.
Indeed, that was great. Fantastic.
Thank you. Thank you.
Wonderful. And
Thank you.
I hope the audience follows your enthusiasm. From my impression of what happened, has happened in India over the last decade and the potential that India has, you're absolutely right. And it is the young people you're talking to who are going to do this. I mean, our next speaker can also talk to this. Spenta Wadia, although not a direct grandchild or child of mine, I feel enormously related to. I've known Spenta since he was a graduate student at CCNY, and have interacted with him with physics and other. But I have to introduce you before you start speaking. So Spenta is a fantastic physicist who's made incredible contributions to gauge theories, to QCD, to matrix models, to string theory, everything. And we've had many, professional interactions, but Spenta and I have also been comrades in arms in trying to, well, mostly Spenta, but I've helped Spenta a bit in trying to develop theoretical sciences in India. And Spenta is the founding director, the initiator, and the pioneer of the development of the International Center for Theoretical Sciences in Bangalore, which is, now how many years old? 10 years old, or maybe a little more, 12?
Yes.
And this is an effort that Spenta asked me to join with him in trying to help create, and I was happy to do the little I could do to support him. But it really is an enormous triumph of will. It's something new in India, and it's enormously successful. I'm very proud of the little I could do to help it succeed, but Spenta deserves the credit. Spenta has also been involved in exactly what Sandeep brought up, the new efforts of the government of India to reform education in India from kindergarten through universities and research institutes. And I hope he will speak to that. Spenta and his friends who put together this incredible document outlining a strategy and a plan for the next 10, 20 years, really did an amazing job, and hopefully some of that, or most, or all of that plan will be implemented soon. And it addresses some of the issues that Sandeep brought up. And so, Spenta, please.
Thank you, David, for this very kind introduction. And I have these slides, and I'd not very good at speaking extempore, so I prepared slides. That's the reason.
But Spenta, can you play instead of, because I'm not sure they move unless you play. At least they didn't on my panel. You haven't gone. You have a PowerPoint.
No, this is the second one. This is the second slide. Can you see it? I can move it on the left. There's a panel. Can you see it?
I see the first slide. It doesn't move automatically unless you play.
No. Yes. That's what I did actually. Now, can you see the second slide?
Yeah.
Yes.
Okay. David, can you see it?
Yes.
Okay. All right. So I have, in response to the questions which were posed by the panelists, I have prepared a few slides basically divided into three parts. So one is something about basic sciences, then about where India is in basic sciences and related areas. And the third part will be about our own subject, string theory. So this is because there's a large audience of students and other practitioners, including people from the humanities, I think, that are watching this. Okay, so as both Kamran and Sandeep and all of us, I think, will emphasize, we are also curious about the world around us. And few people would deny the importance of answering questions like the origin and fate of our universe. How did it begin and where is it going? Also about the origin and evolution of life on Earth. How did life happen? And how did we happen? And where are we going? And then the third question, which I have felt very deeply about, is how did matter, after all, we are material stuff, organize itself to think? What is the origin of intelligence, etc.? So these are questions which everyone in our species will respond to as fantastic. So basic sciences and mathematics are involved in the quest to answer these and similar questions. Now, the history of science shows us that most scientific discoveries owe to serendipity and curiosity-driven free will explorations that create a repository of knowledge. This is in defense of basic sciences, which do not get applied immediately. And this accumulation of knowledge, this bank of knowledge over varying periods of time, often translates into technologies that elevate human life, as we all know, and in turn enables new probes of the natural world also. So there's a feedback loop here. The invention of the Hubble telescope led to a great discovery of the expansion of the universe, and so on. But scientific knowledge need not be immediately applicable to real-world needs like healthcare, transportation, communications, but eventually it does, as was also emphasized by Kamran in his presentation. Now, I have one very slide to illustrate this point, actually. To illustrate, the cell phone is a great example of the march of fundamental science all the way to technology, all the way to the 600 million people in India that actually have this instrument. So, I mean, so obviously the story begins with the discovery of the electron. And this is a famous plaque in Cambridge University, which once Rajesh and I actually were very fortunate to have a look at. And we really enjoyed looking at this plaque. It's about J.J. Thomson and the discovery of the electron. Then came, of course, the great revolution of quantum mechanics, the Dirac equation, and that also led to further understanding of elementary particles because it predicted the positron. So you have the electron positron. Then there were applications of this around 1947 with a lot of developments by these famous gentlemen, Bardeen, Shockley, and Brattain, which gave us the transistor, which revolutionized life as we know it. And then, of course, there is the mathematician, engineer, Alan Turing, who wrote his famous paper on computable numbers in 1936, and Claude Shannon. And all of these people, actually, all this work contributed to the making of the cell phone. And I've also put here Herr Einstein's famous equation, because this is the one that enables you to have a good GPS connection. So this is the point. 1897 and to our times is more than 100 years. And you see what you call fundamental science slowly actually, in an innovative way, became applicable to devices which are so common to all of us. I just wanted to make this point of this issue of separation between fundamental science and applications needs to be understood in a historical context about the time scales in which this can happen. This is very important for Government of India, also in New Delhi. This particular point, that you cannot deliver doing basic sciences in a very what shall I say, that small time scale. Okay. All right. So this is about basic sciences. Now I want to make a few points about research in India. So in the past, India has made civilizational contributions to mathematics, astronomy, medicine, philosophy, etc. For example, the use of zero, negative numbers, the invention of the algebraic ring, algebra, trigonometry, the triangle theorem, calculus. These are all contributions that came from our country. And here are our times. We also have very great contributions. Ramanujan, Raman effect, Bose statistics, Bhabha scattering, Saha equation, Chandrasekhar limit, and it goes on and on. So that's about our past. And of course, today also there are some very important contributions, which I am not going to name here because some of those people are in the audience. So it's not to embarrass them, I will not say that. But let us have a look at India's present science and innovation investment and capacity. So these are numbers which are taken from the National Education Policy, from the DST, the Economic Survey of India, and AISHE, etc. So most of these numbers apply to something like 2018. So research and innovation investment is approximately only 0.69% of GDP in 2018. 82% of this is consumed by 5 agencies of the Government of India: the DRDO, the Defense Research Development Organization, the DAE, the Department of Atomic Energy, the Department of Space, CSIR, and the Indian Council for Agricultural Research. Amazing, amazing numbers. There's a steady decline from 0.84% of GDP in 2008 to 2018, which is 0.69. This is very important to observe, this decline. Now, corresponding numbers in China are 2.1% and the United States 2.8% of GDP. The second point is something which I think Sandeep also alluded to, is that the number of researchers per 100,000 in India is 15. It is 111 in China and 423 in the United States. This is amazing, right? 10.8% enrollment in masters we have, and 0.45% in PhD. So we have approximately a very small number of people actually coming into higher education and then into research. So less than 1% of the 40,000 institutions of higher education in India engage in research. And there is very little research in universities and colleges across India. And as Sandeep emphasized, unless we get our act together about increasing university and college-based research, we will not be able to scale to the level that we would like to make India a power which discovers and then makes in India, as David has very rightly put. Just to end this particular slide, the American Physical Society has a very important report in 2019, which David definitely knows about, and he has shared it with me, that industrial physics contributed 12.6% of US GDP in 2016. It's a whooping 2.3 trillion US dollars. And direct employment generated was 11.5 million jobs, which was 6% of total US employment. These numbers we should contrast with ours, and we should set a benchmark to really increase in scale our education, our research, and the number of people doing it, and also the investment of the government of India. So as Sandeep also already mentioned, that one of the arguments given by the government is that yes, this is the GDP investment. I mean, even after you take out this 82%, but where are the people who will do it? So I think we need to scale up both on resources, which are government resources, also involve private people, and also on scale up the number of people who are engaged in basic sciences and technology and engineering. And yeah, so this is a slide about the state of India. And now let me come to our subject. This is the third and last part. And so string theory is really a name that is given to a framework of physics. It's not just some one-dimensional string that's dancing around, but it's just a misnomer to a grand new framework of physics, which is very new and which really, in a sense, discusses very many extended objects also. And it addresses questions of gravity and particle physics, beginning in 1968 with Veneziano's famous discovery. And what are the questions? And I think Sandeep and Kamran have already alluded to. We are all the same, very, very similar things. We were all from the same root. But good things said often are not harmful. There's a good outcome of redundancy here. The questions: the origin and the evolution of the universe, the energy budget of the universe, which is approximately 95% dark energy. This is the negative pressure that David alluded to. This dark matter. Why is the universe so large? Why is it so flat and not so curvy all over? Then the unification of the theory of elementary particles and interactions with gravity. Are there new elementary particles and interactions beyond the standard model, which has been so beautifully verified experimentally? And there's the issue of resolving the conundrums posed by Hawking radiation for black holes. It's a big development. And then, of course, there's an issue of the resolution of the singularities of black holes, and technically maybe related the singularity of the Big Bang as we move backward in time. And yeah, so these are some of the questions which string theorists are really involved in. This is the big picture. Now, these problems are very vast in scope and very difficult. And there are times I have also wondered, like Sandeep, whether humanity, we have finite processing power, actually, as a species, plus our technology, whether it is possible really that this huge thing around us is really, in some sense, understandable or computable, or I don't know the answer to this question. But it's a very interesting question. But however, the efforts to solve them have yielded a rich dividend of connections with many branches of physics and mathematics. Okay, so, all right. So in some sense, string theory is really an interdisciplinary unifying activity in physics. The rich structure of string theory makes connections with many areas of physics and mathematics. Elementary particle physics, condensed matter physics, fluid dynamics, statistical mechanics, information theory, random matrix theory, chaotic dynamical systems, geometry, topology, etc., etc. It's amazing, right? That many of us really have understood and even contributed to such a diverse areas of physics, which in my opinion is one of the most satisfying things I have found as a physicist, as a string theorist, actually, that this diversity is available to us to contribute to enjoy. Okay, so just one more thing, actually, before I end my presentation. Because we are scientists, the question of experiments, as Sandeep was alluding to, is very important. And it should be said that presently there is no prediction that can be directly tested in string theory, directly tested. The theory is too incomplete, and I've forgotten to complete this sentence, and takes a lot more work, maybe for a very long time. Now, experimental evidence for gravitons via precision CMB experiments is a possibility in the future. There are other graviton detecting experiments which are also being planned by people whom I have talked to, and to be able to somehow get a signal of the quantum gravitational radiation from the very, very early universe. Now, patience is of essence here. And please recall, it took almost 100 years from prediction to observation of gravitational waves. And this subject is just about 50 years old. The discovery of supersymmetric particles in future colliders may also make string theory a compelling candidate for the theory of the quantum world at extremely short distances, like 10 to the minus 35 meters, a theory which you need if you want to understand the very, very early universe and where we all came from. Okay, so my call is to support string theory research. Why? It's a powerful new framework, just over 50 years old. It has the tenets to be a theory of quantum gravity and the early universe. It connects many areas of physics and mathematics in a deep and compelling way. It is not a fringe activity. It is not a fringe activity, and I can elaborate on that a little bit later. As experimental methods progress, one will need a theory to frame the right questions and observables. It would be valuable to establish a virtual center or an institute in large educational institutions in India, which can encourage interdisciplinary research in physics, mathematics, and engineering. And the string theory people can play, I'm sure they can play a very, very important role. And we are experienced at the ICTS, as Rajesh and I witness it all the time, the great involvement of the string theory people with other areas of physics. So this is a slide in support of string theory. And I want to end my presentation with a quote from David Reich, who is the author of this famous book, Who We Are and How We Got There. David Reich is a scientist, computer science biologist at Harvard University. And I have adapted his quote, actually. I have removed some words and put in mine. Shouldn't intrinsic curiosity be valued for itself? Shouldn't fundamental inquiry into how the universe came about be the pinnacle of what we as a species hope to achieve? Isn't it an attribute of an enlightened society that it values intellectual activity that may not have immediate economic or other practical impact? The study of the universe and its evolution, as of art, music, or literature, is vital because it makes us aware of aspects of our material origins that are profoundly important and that we heretofore never imagined. So thank you all very much for listening. Hello, I'm not hearing anybody.
We have lost David.
Yeah, looks like we have lost David.
Oh, that's unfortunate.
So can I just make a suggestion? Maybe Sunil can take over and make his presentation till David comes back.
What did you
Or
want?
somebody can, yeah.
Oh, to just moderate? Yeah, sure. I mean, we have to wait for David to come back. So Suresh, can you remind me who was the next speaker? There was a list.
I think it was you, Sunil.
Oh, okay. But I think we really need to wait for him. Do people, organizers, do you have like his phone number or something?
Unfortunately, that's not the case. Unfortunately, that's not the case. So
I think it's just a matter of few minutes. I think
Mani will have David's phone number, no?
I have his
I'm
number.
sure,
I'm
yeah.
calling him.
Penta has it. Penta, call him, please.
Yeah, I'm calling him. I'm calling him.
What we might do, I think, is okay. I don't know. The organizers, you have a plan for everyone to speak, and then only have audience questions.
Yes, that's the way it is. So, but yeah, but I think Mani can call David and just see if he's back in 1 or 2 minutes. I think people can wait.
I think Spenta might be calling him.
I'm calling him.
Either of you welcome to call, or Kumrun.
Yeah.
I see David. David is back. Welcome back. Yeah.
So I guess Penta finished.
There you are. Oh God, we thought we'd lost you.
Well, you did for a while. The internet connection halfway around the world isn't always good. Spenta, have you finished? Did you come to the end? Did you come to the end? Okay. Given the time, I suggest we move on. And our speaker is Shiraz Minwala. Is here. Let's see.
Hi. I think on your list, David, you had Sunil before me, though I'm happy to go first.
Actually, you are absolutely right. Sorry. It's yeah, indeed. Sunil Mukhi is next. I called it him before as a representative of ICER. Sunil is what is a distinguished theorist, a string theorist who's done lots of work on various aspects of string theory and the mathematics involved. He gave a beautiful talk on rational conformal field theories at this conference. But I called on him before because he had moved from the Tata Institute 8 years ago, I think, something like that, to the new ICER in Pune, one of these new Indian institutes of science, as opposed to engineering, which has been set up recently. I think there are 5 of them now. And I had the great pleasure of visiting Sunil in Pune a few years ago. Very, very impressed by that ICER. Really was world-class experimental physics and other sciences with a very innovative and exciting educational program. It really was very impressive. I hope very much that I'll be able to come back and see how things have progressed since then. So Sunil is, hopefully can tell us about the ICERs as well as address the other topics that we're discussing. Sunil?
Thanks so much, David. It was wonderful having you visit us. This is already 5 or 6 years ago, before our new campus had really got very far. And if you come now, you'll find that the tree which you planted has reached quite a significant height. And it's right there in front of the guest house. And everything has changed. I mean, everything's bigger and everything's doing great. And, what I feel proud is that, people from various departments, for example, this year biology got this Bhatnagar Award, which is like the highest research award for young people under 45 in India. And, other people have been elected to academies and made fellows and made associates. These are, of course, they're only awards and only recognitions, but they do tell us something about where the institute is going. And we've also raised quite a significant amount of private funding, let me say. One of the great things two great things are happening right now, maybe 3. One of them is that we're building a new center for data science, which is going to bring together people in mathematics, biology, physics, chemistry, and computer science, of course. And it's a huge grant we've got from the Mehta Family Foundation, which is based out of Texas. That's going ahead. We have a new center just approved for water research. It's a center on water management. Okay, water history management. But that's, these are wonderful things, but these are not part of the present discussion. And I have a very small, I probably only take 5 minutes, a small list of points to make, which are pertinent to the present discussion. First of all, about string theory, very good things have been said by all the previous speakers, which I heartily endorse. But I want to add something in the direction of breadth. In my view, we are part of 1, high energy physics, 2, gravitational physics, 3, strongly coupled physics, 4, quantum information physics, and 5, mathematical physics. At least you can add a few more to this. I believe we should always acknowledge and own these roles. There's no admission fee to be part of any of these communities, and we should acknowledge and own all of them. I think some of the slights and negativities we've received from people are often because we fail to acknowledge our role and responsibility for the well-being of these very well-founded and historical physics communities. Okay, now many people talked about the wide applications of string theory. For me, I think in this whole conference, a talk which just felt really thrilling was the first talk by Zvi Bern, because his calculations are relevant for the LHC and potentially also for gravitational waves. Now, I know from the point of view of the public, maybe big experiment is a big experiment, but LIGO and LHC do not live in the same universe. And it's amazing that any person can do a calculation that's useful for both. I think that kind of broad sweep is characteristic of our field. So I think breadth is something we should participate in, enjoy, rejoice in, and also own. This is one point. The second point has to do with my ICER experience. And a question that was asked by the organizers, is it important to communicate what scientific results are achieved or how science is done? And I would certainly go with how science is done as a major communication point when we talk to people. It really fascinates the undergraduate students I teach. Right now, I'm struggling with a class of 200, many of whom are very brilliant, who are arguing about what is a back of the envelope calculation, what is an order 1 estimate. It's making them crazy. They're trying to accept it. They have some instinctive rejection of it because I think they've been brought up to think of physics as an exact science, and estimate numbers, rough orders of magnitude, they find it very challenging, and I think that challenge will make them actually much better scientists. So I think how science is done is, for me, the great thing that I can communicate to students. The last thing I want to talk about is outreach. And here I want to point out that, many of the other institutes represented here have done a lot for outreach, but we should a little bit think about where we stand in India. All of us in this panel are in the top 5.5% economically. We are all in gated communities, myself included. We are all in privileged institutes, myself included. But sometimes, when you step out, you learn things that you don't read about. The giant meter wave radio telescope near Pune attracts 20,000 visitors at its annual science fair on February 28th. And they come in various vehicles from bullock carts to Mercedes-Benzes, and they are everything from farmers to business. I should emphasize that in this part of India, it's the farmers who come in the Mercedes-Benzes, but okay. It's such a diversity, but that diversity consists of different lived lives and different languages. So if we want to reach them, outreach in English surely is not the way. Outreach in any of India's dozens of languages is extremely important. The press is doing that, of course. There are a few but very good science journalists in India. Some are present today. I've heard complaints from them that we people who work in these elite institutes are often not very keen to talk to them unless we are able to advertise our own work. That's unfortunate. I think we must advertise science on a much broader canvas than just what we do. Okay. Now, one of the most receptive constituencies of the public is high school students and school and college teachers because of the amplification effect. If we reach them, they reach a factor, much higher factor exponentially of more people. And I'm very proud that my institute has both public and privately funded outreach, ranging from gravitation to laboratory physics to data science to epigenetics to water systems, which I mentioned. I think these are extremely important, and our community should actively participate. Okay. The last point I want to make is about how to communicate research in gauge theory and gravity. My sense is this panel is people who work in gauge theory and gravity largely, and of course Dr. Mani Bhaumik, who's a supporter of this activity. And we often talk about black hole physics as if it's abstruse, but basic quantum physics as if it's something very well known. From our point of view, it is. But for the public, both are equally abstruse. And I do think actually that our community can be particularly effective trying to propagate mysteries and wonders of the quantum world, and not only the world that fascinates us personally, which is more like the world of cosmology, the world of gravity, and so on, just the quantum world. And I think the public is, as Sandeep has emphasized, the public is very keen to hear about this. But I think, again, I'll make a request to us to broaden, try and reach more people in numbers and more in diversity as well. So I think I'll stop here. Thanks very much. And last thing, David, thank you for all the inspiration you've provided over the years. And I just want to highlight one thing. I was going to start with that and I forgot. David has this fantastic article, which is called Why China Should Build the Great Collider. I'd like everybody to go and read it. A rebuttal to CN Yang, a response to CN Yang. And David has said in his words what he thinks a developing country should do, can do, what it will benefit from. Almost everything he's said applies in some form or other to India also. And I again want to thank David for having that breadth of vision, which encompasses not just the US, but the entire world. So I'll stop.
I don't think it would be bad if India were to build a high energy collider as well, but maybe not
after the neutrino observatory.
First, the neutrino observatory. And then the gravitational wave detector as well. That's also an important contribution India could make.
Yes.
But yeah, thank you, Sunil. I think we're going to move ahead because we want to leave some time for questions. Unless anyone, this is not a shy group, who wishes to comment on what Sunil said or what Spenta said.
If I can just come in, David, very briefly, and pick up on what Sunil said, I think it's extremely important, I agree, to convey much more and connect to the much wider audience than we do. And I think some of the learning from COVID, if I may say, the entire COVID experience should help us. Because I think scientists have gotten used to now preparing websites where at least some of the science pertaining to COVID is going out. But I think that should be broadened much more. Rajesh can say a little bit about what we are doing in the TFR system, etc. But some of that can be broadened much more, I think, and reach out in local languages and so on. I think it's a very important. Sorry.
Right. Yeah, there's a lot of room for the use of the internet in expanding knowledge, outside of these very small enclaves of higher education. So let's now turn to Shiraz Minwala. Shiraz is perhaps the most energetic of all the physicists in India or the world. He's known for his enthusiasm and his of interest across the subjects that were the subject of this conference of string theory, quantum field theory, He's dipped his toe into every aspect of string theory and quantum field theory. And Shiraz, show some energy. It's late at night. You need to awake.
Okay. So thank you, David, for the introduction, and excellent. So perhaps I can start by taking us back maybe 1,000 years. How would the world have appeared to us maybe 1,000 years ago? It's a world in which stuff happens, and there are some rules, there's some regularities, the sun rises every day and so on, but largely just stuff happens. A world full of diverse phenomena, each phenomenon seems to have its own rules, and things happen, and that's the way it is, most people will. Now, over the last 1,000 years or so, and perhaps acceleratedly so, we've understood something completely remarkable. We've understood that everything that happens in the world is governed by mathematical rules. Perhaps even more remarkably, the rules that govern what happens in the world, simple rules, simple enough for creatures as limited as us to understand, to appreciate, to write down on backs of envelopes. It's a remarkable thing about the universe that we live in, that phenomena that happen are intelligible. Why should that have been? I mean, it's far from clear that that's right. It have happened. It happened. It's true. Okay, we've got used to this, but I think we should remember how remarkable it is. That the world around us is governed by mathematical law, mathematical law that is simple enough for us to understand and to work with, and even to intuitively understand. You know, not some crazy equations you put on a computer, but you can understand it, think about it, work with it, imagine it. Okay. Now that we've understood this, scientists of various sorts, including scientists in string theory, in my area, and various others, now feel ambitious enough to be able to try to apply mathematics to deep questions that Umron and Sandeep and various other people, Spencer, various other people alluded to. You know, questions about how did the universe begin? Where did we come from? These questions, which for most of human history, of course, excited humans, but have been in the realm of philosophy. You know, in the realm of say what you want and nobody can contradict. Have now become questions that we perhaps can address with mathematical equations, and perhaps can address with the standard of the standards of truth that we've grown to accept in science. And I think this remarkable thing is, for me, a fact of wonder. And how remarkable it is, we shouldn't forget. And in our communication to people outside the field, this is one thing I think we should constantly communicate. The fact that this crazy world is actually governed by mathematical law that we can understand. It's totally amazing. Now, this brings me to the next thing I wanted to say, which is this. Around us in the study of science, especially in the study of mathematics, but also in the study of science, of the more exact sciences, we have a notion of correctness. You know, the questions about which you can be right or wrong. And the fuzz area between being right and wrong is very narrow. Okay. In most areas of normal human discourse, people are allowed to say things. Somebody is allowed to contradict them, and you agree to disagree because there's no very sharp criterion for being right or wrong. In science, especially in mathematics, but certainly in science of the kind that we do, well, the kind that all good scientists do, there is a criterion for a relatively sharp criterion for being right or wrong. And that lends us to a relatively sharp criterion for truth. I feel this is one of the ways in which scientists are valuable to society, because we have a sharp understanding built on our own work, built on our discussions with other scientists, built up a culture in our field, a sharp appreciation of the unambiguous nature and the relative relative absoluteness of truth. I feel this is particularly important today. In the world today, in which when you look at public discourse, especially I feel over the last 20 years and all over the world, but perhaps especially in my own country, India, discourse and truth seem to be almost two different statements, and truth seem to be almost two different things. People construct their own truths. The communities believe what they want to believe. Evidence has little connection with what you believe. You know, the fact that scientists are used to working with systems of knowledge in which truth is a relatively absolute is a valuable thing. And I think this is one role scientists can play in helping potentially play in helping public discourse, to try to inject, to the extent possible, as much a notion of evidence and truth and rigor into discussion as is possible. I don't really have any very clear suggestions for how to be effective about this and so on, but I feel this is a very important thing, and that the fact that we appreciate this as scientists should help us play a role in society about this. Now, this takes me to my next point, which relates to one of the questions that was presented in the list about communication. The question was about how we should communicate our science, and many people have said this before. Some people in particular, but I think the key element, the key adjective I would use for how to communicate is to communicate honestly. Do not oversell. Do not oversell what we have done. Do not oversell what the promise of what we're going to do. Say clearly what we've done. Emphasize what we have not done. Emphasize the failings, and yet convey our enthusiasm and our hopes and our dreams. And I think that is enough. I think that's enough because people appreciate honesty, and they appreciate questions and ambition, and it's enough. And it's much more effective to be 100% honest. It's like Gandhiji, you know, be undersell 100%, 50% rather than overselling 50%. This is important for effectiveness. It's important for our personal integrity, and it's what will in the long run help. It's also important because, as I said, one role we can play in helping shaping public discourse about things that are not science is because we appreciate. We in our professional activities appreciate truth. However, if once we step outside our professional roles as scientists, we start being lazy with the truth, then we lower our credibility. So we must have complete and 100% integrity in how we present our science, and actually complete and 100% integrity in every other field of life. For instance, we must not bow to power. We must not let positions and money and so on influence what we say about science and about everything that is important. We have to be have 100% integrity, and that is what will help us perhaps stay effective in a role in science. Okay, I have one last couple of things to say, and that is this. One of the questions that was posed in the question list of the organizers, the thoughtful question list that the organizers provided us with, was what are the advantages of a developing country funding science, and what are the advantages of something like an IIT funding science? And I have two things to say about this. Many people have addressed this. Two things to say about this. Especially in India, there is in my opinion, there is a great advantage to doing anything as long as you do it excellently. If you do something at a world-beating level, it doesn't really matter what it is. If you're a computer scientist, or you're doing something at a world-beating level, so that people acknowledge you as a world, you or your group or your Your country is a world leader. Experts from outside come to India to learn from you, from these much richer countries, these countries where have economically much more prosperous. I think there are great benefits to us for that. It helps us in so many ways, including helps us with our national, with a sense of pride. If you look around you, I think a lot of the discourse we see around us is fueled by the fact that Indians have relatively low self-esteem. And anything that makes us proud is something that helps. There are bad things that make us proud. This could be a good thing that makes us proud. Doing anything excellently has great value. And I think that for some odd historical reason, we do some of our string theory excellently. And just that has reason about it. Okay. The last thing I wanted to say is about the connection to the IITs. So the question was, why should the IIT, being a technical institute, support fundamental research? Oh, I just want to give you my own experience as a student of one of the IITs. It's not IIT Madras, but IIT Kanpur, the best of the IITs. Sorry. Yes. Yes. Okay. When I was a student there, there was this almost caste hierarchy system in the IITs, in the sense of your joint entrance exam rank. If you gave me the joint entrance exam JEE rank of any student, I would tell you with 95% confidence what field that student was studying. Top 100 computer science, 100 to 300 electrical engineering, and so on. Okay? There was only one subject in which knowing what the student studied didn't tell you what rank was, and that was physics. People studied physics because they wanted to, not because it was the most profitable thing. Okay? And that and various other things gave the physicists in IIT Kanpur, physics students, but also the physics faculty, a great deal of respect. The brilliant computer scientists and other people, and many of your fellow students were truly brilliant people, somehow held a great deal of respect for the computer scientists, as students, but also the faculty. They would ask us for advice on various things. They would try to learn how we thought about problems. I believe that some of them have managed to imbibe some of that way of thinking, some of that culture of physics into their own work. I know a friend of mine, for instance, who studies quantum computation after being a computer scientist. That's one example, many such examples. Okay, so I think this connect, this fact that you have pure scientists, students, and engineers as students in the same institute has a wonderfully beneficial influence across the board in culture. And these things are hard to quantify. In my personal experience, are very important. Okay, that's all I wanted to say. Thank you.
Thank you, Shiraz. Very interesting. Any comments from the other IITs, not Kanpur?
Yeah, can I come in one thing, David, if I may, which is I want to say this especially to all the IIT students who are listening. Don't get put off by Shiraz's comments about IIT Kanpur, but Shiraz is a wonderful example, I would say, of what you can achieve if you go into science in India today. Of course, he's a role model for me too, but I think especially for all of you. And what he said about conveying one's work with enthusiasm, but not overselling it is very important. He does it in his public talks. You should hear them. They're all on YouTube, and I think you'll feel really inspired. Okay, I just thought I'll say that to everyone. Go ahead.
Right. Yeah, and I think, Shiraz made a very good point about what is special about our culture. And I think that is something that we need. I think Sunil also talked about this. It's not just the details of our science, which is fascinating and wonderful. About it, Can you hear me? Connection is tricky here. But also just the scientific culture itself, which we've, educated in and follow our daily life. And it is a very special culture. The scientific culture based on the scientific method, extraordinarily powerful. It also, has certain aspects that have a much broader importance. It's tolerant of new ideas. It does not respect authority. Anyone can question anyone. The only judge is nature, not society or politicians or religion or ideology, but nature is the only judge of our ideas. And because of that, we have learned that it is very important to tolerate transparency and tolerate dissent and different opinions, and and especially to be open and honest, as Shiraz said. And those elements of scientific culture have, many of us think society would benefit if they were to adopt them more widely. And I think we can help try to transmit that culture in a much broader sense to society. Let's go on now. Last but certainly not least, to my actual child, academic child, one of my students, whom I'm very, very proud of, Rajesh Gopakumar, who is now the current director of the International Center for Theoretical Sciences in Bangalore, ICTS, and is doing a magnificent job leading that institute, especially through these very difficult times. And manages still to do incredibly interesting, groundbreaking physics, which he talked earlier in this week about. A very beautiful and exciting talk. Rajesh.
Thanks, David. As always, as I said at the beginning of my talk, it's been a privilege in my life. I think from 1992 when I joined Princeton, and 93 was when I actually joined David as a student. It's been a privilege these last 27 years to sort of be with him. In the Indian tradition, the guru is someone who not only mentors whatever you are, whatever the technical subject you sort of specialize in, but sort of is the world view and the broader outlook on life gets shaped, and that I think David has done both in physics, but also through the support for science in India, string theory in India, science in India, and more specifically ICTS, where in the last 5 years. So thanks very much. And I think it's great that, it shows David's passion about science in India, that he has agreed to, that he's chairing this particular discussion. So I'm thankful to the organizers for putting that together. Of course, one advantage of coming in after a galaxy of the panelists like this is that I don't have to say very much. I think most of the non-trivial things have been said already. What I will sort of just have to say are more the nature of postscripts and sort of, as Spencer said, emphasizing through redundancy a few things. So there were sort of three themes I could kind of discern in the set of questions that Ian and others sent us, and which have been in the discussion. So I'll try to sort of sort of share some thoughts on each of these themes. So, the first was sort of science in India broadly, fundamental science and so on, and then string theory as a subject and fundamental physics of that nature, and finally science communication. And I think all these three are very important ingredients in a scientific scientific community and so on. And I think talking about these, I think has been very healthy. So about science in India, maybe starting from there, it's sort of going to what Shiraz and then David just said about the culture. And I just want to remind the audience that I think India is one of the few countries in whose constitution is written the idea of cultivating a scientific temper. I think this was a phrase Nehru, and which I think he was very committed to. It appears in his writings quite early, and it found its way to the constitution. And you heard about the IITs being the brainchild of Nehru and so on from Mani. So this culture is there, and in fact, it was even before independence, in the pre-independence surge of science in India. And Spenta mentioned some of the names. That I think was a reflection of a desire to sort of push at the frontiers of knowledge of a country which was, of a nation which was sort of emerging from many years of sort of servitude and so on. So that spirit, I think, that was there in pre-independence India. And at that time, in fact, if you see the works of Saha or Bhabha or Bose and Raman and so on, they were not thinking about will this have an immediate application to solve the problems of India? But they realized that it was important, nevertheless, for India, for institutions to be created, for good science, frontier, cutting-edge science to be sort of developed in India. And it was it creates, as Shiraz also said, a sense of confidence and a sense of capability when you realize that the frontiers of knowledge are being pushed in institutions in the country. And I think this is very important, and have to continue that tradition. And in some ways, this is where it touches on string theory as well, since string theory has in India had been, for various historical reasons, which has succeeded in pushing the frontiers. And so the kind of proof of concept that this conveys to the public, I think, is very crucial. It's an intangible sort of a thing, but it is something, I think, which should be valued and which should be preserved. But even after saying that, as Sandeep mentioned, the funding agencies are not always going to be convinced by intangibles. And I think it is important to also emphasize that even highly theoretical abstract research is part of an ecosystem of science, and you cannot sort of remove or excise in some top-down way that this is not the kind of science we will be doing as a country, and this is the sort of science we should be doing. It never works, because it's like an ecosystem. It has a sort of a diversity, and each element, however sort of tiny, is integral to the sort of health of that, the health and the continuation of that ecosystem. I mean, my son likes this documentary called Secrets of Our Living Planet. And each of these has an episode in which this person, the presenter, he takes some ecosystem, and then he says, why is, for instance, one was on the Sundarbans, and he asks, why is the crab in the Sundarbans important for the Royal Bengal tiger? And then he takes you through the whole web of the ecosystem. Why, without the crab, which plays a certain role in toxicity, I mean, it's a very complicated for survival of the Royal Bengal tiger in that ecosystem. So there's a complex chain, and string theory, I think, has a role to play in that big ecosystem, because the sort of ideas that frontier science produces, both theoretically in things like string theory, but also in experimental science, the frontier areas, the gravitational wave physics or INO and so on. I think these have a sort of, by pushing technology to an extreme, by pushing ideas to an extreme, I think you are advancing knowledge. And this is something I think, even from a purely utilitarian point of view, I think it's important to communicate that. So, so talking of communication, I think I think again people have said very much about how science communication and communication in general should be, but in India especially, and Sandeep alluded to this also, I think that we have a sort of in conveying the scientific temper. I think there's a sort of a dual role we play as scientists, not only in conveying the excitement of science, and the sort of the sense of wonder that it evokes. That Kumran also said, this is something we see whenever we communicate science, but it's also important, the scientific temper that I mentioned in the Constitution, how science is as a way of life. And the public, very often we tend to sort of communicate the end product of a lot of scientific development, but not the process. And the process is full of pitfalls, it's full of dead ends and many things, so turns, etc. But I think there's a value to communicating that nuanced understanding of the scientific method. It's an open-ended process. It's a kind of a continuing process. It's an ever-enlarging process. I think this is something I feel is something we should be having, even if not explicitly. But I think it's good while communicating to keep this in mind, and that leads to that questioning spirit. And this is coming to another point of the lack of human resources in India for our science projects and so on. I think we need to get young people enthused, and showing them the way in which science progresses is a good way to capture that enthusiasm, and to give them the feeling that there are all these questions, these wonderful challenges ahead, and in our country, in India, for students who are interested. And I think this is something we need to sort of plant the tree for future generations, as the Persian poet said. So that's I felt about communication. And then the idea of communicating in Indian languages. I think we don't do enough of that, and I hope that we can engage. And in the TIFR system, we have been starting on that in this COVID process, and we have this website called COVID Gyan, which is now in 12 different Indian languages. And it was sort of a volunteer effort by scientists across the TIFR and IISc system. So I think you could see that there's a desire, but we need to channelize that. So I think I should sort of end there. I just wanted to also say that it's been a privilege in the to be a part of the Indian string theory community, because it's been sort of a very supportive sort of community of closely knit people who sort of have the goals of advancing science in India very close to their hearts, and the culture that prevails, I think, hopefully will get transmitted wider, and the scientific community in India, as it grows, hopefully will show a sort of a different way of doing science, which is sort of carries people along in a very inclusive way. So that's one thing I wanted to add to the string efforts, to the things about the string efforts in India. And I think IIT Madras would do very well to to set up a center for theoretical sciences because, for some reasons, things like Shiraz said, for students, but also in terms of the research across the engineering disciplines, and having that scientific and theoretical sort of a think tank on campus, I think, is a very valuable, a very valuable sort of a resource, which I hope they will proceed to put in place. So yeah, so that's more or less what I had to say as sort of addendum to things. So thank you.
Thank you very much, Rajesh. I think instead of opening up the floor to ourselves, let's open up the floor to the viewers. I know there are reporters and other viewers who want to ask questions. Ayan, are you there? And,
yes, yes, I'm there. But I would leave to Arul to read out the questions from reporters and many other people from the audience too. Arul, over to you.
Thank you, Ayan, and thank you very much, Professor David Gross, and to all of our panelists. It's been a really fascinating couple of hours, and many opinions and facts have been put forth. Let me just introduce myself, because I'm not really from the community of string theorists. I work on quantum information and on quantum chaos. And if I may just add a couple of words before coming to the many interesting questions that have been posed. Since I come from the quantum information community, but also I'm a theorist, I've been kind of, shaken away from my, cocoon in a particular way, which I think is kind of relevant to this particular discussion, because society, through the arm of the government, not only expects of us something, but in fact demands of us certain things. And in the quantum information community, that is today a quantum computer, so there is a huge amount of, as you know, funding and effort going on throughout the world and including in India. And there is a whole upheaval, not only in India, but throughout the world in terms of, I would say, even resources, academic resources, because with the influx of big industrial players such as Google and IBM, Microsoft, you name it, they're there in this field, and that's also changing this thing. So I mean, we are in a particularly interesting era now, and as the string theorists have mentioned, with their input into this field, it's actually now that's another way in which we are, interacting very strongly, I think, with society. And we can't really see the future. That's what is interesting about science. But this is something where we are starting to interact extensively with, technologies, society, industry, and so on. So it's really an interesting phase at this point. So maybe we will, maybe some of the panelists can also talk about that at some point, but sticking to my role here as actually to facilitate discussions because of this particular mode of our interaction. I'm going to start with some questions. I think there are two from journalists. One of them, Shubhashri Desikan from the Hindu newspaper, had to leave for another meeting, but before that, she asked this question, whether it's a good idea to centralize control over funding and research. So I would leave it to the panelists to respond at this point. So it's about centralization.
Do you want to take this, since you're involved in this NEP? Should research all be centralized and run from New Delhi?
Well, research funding especially.
Well,
I think it would be good to have research funding not with a single in a single agency format. I mean, just like in the United States, research is funded by NSF, the Department of Energy, NIH, etc. I think in India also we need to have various agencies fund research on a competitive basis. And I think this would be very, very important actually to have multiple agencies fund.
One question is
research
where the money comes from. The other question is where does it
I cannot hear you, David. Can you repeat, please?
You can't.
No.
So, in the United, can you hear me now?
Yes.
Yes.
I mean, funding usually has to be centralized in one or many agencies, but the actual decision as to what is funded should be as bottom up as possible. And that's why the best models of research funding are ones in which the people who decide how the money is spent, to some extent, are the scientists. Either, like in the Max Planck Institutes, they actually run the institutes, or in the United States through peer review of proposals to central organizations which allocate. Because, you know, science is, it's very hard to dictate science from above. So as Spencer said, it's a good idea to have many sources of funding so that you know, one agency can make a mistake and the other agency can correct that mistake. But it's ultimately the actual working scientists who have to make the scientific decisions about what areas of science are worthy of support. Sandeep, do you want to comment on this question? You need to unmute.
You're muted, Sandeep.
Sorry, excuse me. No, I was saying I would agree with what you were saying, David, and what Spencer said. I think in at least the kinds of organizations I know about, you know, these are connected more to the Department of Atomic Energy. So I don't know how it might work with other kinds of agencies, but it's very much what you said. There's a decision made about a certain amount of block funding by you know, centralized agencies of the government, and considerable discretion is left, say in the case of TIFR, to the TIFR director for how to allocate that, which is then done on the basis of international peer review and so on. And I think it's a good system. The issue there actually is just the unreliability of fund flow. And really what happens is there are certain budgetary commitments made which don't come through. And it's extremely difficult to do competitive science in that environment of unpredictability. And I can give you more details, but just as an example, you know, the TIFR is, if I may say, one of the premier scientific institutions. And a year ago, we got a 100%, I mean, a 50% cut in our R&D funding with no notice. It went from 200 crores across the TIFR system to 100 crores. You know, you can't sustain world-class science like that. So the basic mechanism is okay, but it's the actual operation, I think, which leaves something to be desired. That's what I would say. Go ahead, I'm done.
Thank you, Sandeep. So can we move on to the next question?
Yes, please.
Yeah. So this is I'm just paraphrasing this question because I can't quite read it from the chat exactly. This is from Mr. T.V. Venkateswaran, who's from Vigyan Prasad, and the question is about the lack of a outreach arm for the Indian scientific community that puts out research that's happening in India. at least in major Indian languages. And he also goes on to ask about the great divide between social sciences, science, arts, and humanities. Because other areas like social science and humanities are really getting a bad deal at the end of the day. Thoughts of the panelists, please.
David, can I respond to that? Hello? Hello?
Yes. I'm sorry, is David? David,
Yeah.
you're muted.
David is muted.
Yeah.
Sorry, having internet problems.
Okay, so maybe I can ask any of the panelists whether they would like to take this up. So one is about the lack of an outreach arm of the Indian scientific community, if that is actually the case, and also the divide between science, social sciences, and humanities in general.
So I can actually respond to the second point.
Yes, please.
Yeah, so this is a very important divide, and it's very unfortunate. So if you look at the national education policy, which has been approved by the Government of India, there is a mention there of the National Research Foundation. And the National Research Foundation will include not only the sciences and engineering, but also the humanities and arts. I just wanted to say that it's there in the NEP policy, which has been approved by the government. Hopefully the National Research Foundation will happen, and hopefully it will do all the things that it's supposed to do. Okay. That's all I wanted to say.
Maybe.
Oh yeah, Rajesh, you should.
No, Sandeep, go ahead. I mean,
No. Okay, very quickly then, Rajesh, I want to hear what you have to say. But very quickly, I was chatting with this journalist in the chat box earlier, Arul, and I think he suggested something which I've also been thinking about. In the West, there are these Eureka alert and so on features which inform the journalist community about important science developments. And why should we not have a similar feature which reaches out to journalists, especially reporting in local regional languages about important scientific breakthroughs? I think I've also been thinking about this for the past year or so. It's good science happens in India. It gets buried in journals. People don't learn about it. And we need a way of sending that up. I think that suggestion of his is well worth taking forward, either through the academies or some other way. I just wanted to say that. Yeah, Rajesh, please go ahead.
No, I just wanted to address this first point again, just some ideas that have been sort of floating around. I mentioned earlier about this COVID GYAN, which was interinstitutional collaboration that of scientists who came together from IISc and the 6 centers of TIFR and Tata Memorial Hospital and several other places and India Biosciences. I think people were driven by the sense of urgency, and we had this website up, etc. It was a very good model of interinstitutional collaboration to communicate science. And we felt from the experience of this collaboration whether we could try to expand it into something bigger, which would not just be for COVID or a specific crisis-driven thing, but more of interinstitutional arm of the various partner institutions, which would engage in a two-way dialogue with society on questions of science, which potentially scientists can address, and scientists give input on many issues that I think, especially in India, could do with informed scientific input. and whether it be it's like COVID or pandemics, but also the environment and pollution and energy use and urban infrastructure, many things. I mean, so one of the nice things was how several people from these institutes started engaging with their respective, using their respective expertise on some of these questions. So more than just communicating science, even having a kind of a dialogue with society in a broader way, a more meaningful way, responding to sort of the things that people are saying, I think is something our institutions could do on a larger scale and better. And perhaps we need a framework or a kind of a nodal institute that will do a nodal sort of a center that will do this. Yeah.
Thank you, Rajesh. I think, well, I certainly hope some of that comes true, and we should work towards that for sure. David is back. Would there be more responses to these questions?
Sorry?
Would there be other responses, or should we move on?
No, please go on.
Okay. So from the other panelists, Sandeep and Rajesh have given inputs on this. So any other panelists would like to chip in?
Yeah, I'd like to say something. I don't know whether this is an opportune time, but I wanted to especially emphasize this point that was made by Shiraz about the idea of truth and its value in social discourse and its value in understanding and evaluating the history of our country. I think one of the main problems, in my view, of what underlies the social discourse today is a misrepresentation of history. And I think if history is also looked at, I'm not the first person to say that. I mean, some very wise people 200-300 years ago have made this point. If history can be understood scientifically, it will actually make a very big difference to our social discourse. I mean, they're really to go after the truth, even about Gandhi, about Ambedkar, etc., etc. I just wanted to make this point that one can extend our scientific methods and our scientific personalities also to perceive the truth of the society around us. Yeah, thank you.
Thank you. Actually, there is a variety of questions. So let me see. I may be mixing up some of the, some of the types of questions, but there is one, I believe, on the YouTube channel, which those of you who are familiar with the landscape of, physics education in engineering colleges in India would be familiar. And actually, the pain kind of comes through. But the basic question is, why are engineering college physics syllabuses so graded? Especially the AICTE is mentioned in this regard. So I don't know how much experience or opinion one has on this, but would anybody like to respond on this? So it's basically that, I mean, a lot of, as we know, a lot of competent young minds in India get into engineering, and they are really interested also in the sciences and physics, and they find themselves usually with a very minimal sort of opportunity to pursue it there. Are there any thoughts on that, panelists?
Can I make a comment here?
Yes, please.
Yeah, so, I didn't fully understand the question, but you said, are the engineering colleges syllabus, why are the engineering college syllabi somehow not so good or not treated?
No, in particular for physics. So
just for physics?
So the AICTE is mentioned. So there is this AICTE syllabus,
sure,
which is ruling all of the
sure,
what happens in
So what is the specific complaint, please?
Is why are actually I believe they are reducing the number of physics courses.
Okay.
Continuous basis. Yeah.
Okay, here I think an important point is that you in any country you can achieve what you can. You can get educated by being in an appropriate institute, and that institute will have its certain, approach to what it wants you to learn and the goals and what you are expected to achieve there. So I feel that, if you're in a college whose physics syllabus is dictated by AICTE and you don't find it appropriate, the best thing, of course, would be to somehow try to go to a different university. And my sense is that the NEP has a little bit more scope. The new national education policy has a little more scope for lateral movement. So one thing which I felt strongly, which I heard about in France, is that you can do year 1 of your degree in place X and year 2 in place Y and year 3 in place Z, and you still get the one national degree, even though you have worked in 3 different. There's an equivalency. So I think the NEP plans to make lateral movement easier, in which case, you have to, if you want to do science, I think finally, you cannot expect all engineering institutes to provide a very rigorous background in physics. I think that's an unrealistic expectation.
I think fair enough, Sunil. Yeah, thanks for the response. We'll move on to some other questions. So one is...
Sandeep wanted to address that question since he urged all the students not to go into engineering, but to go into physics. Sandeep, you're muted.
Sandeep is saying something?
Yeah, no, I'm sorry. I did want to say something here, if I may. Arul, from what I understand, part of the issue here is that curriculum is very rigid. If you are doing engineering, it's a fairly rigid curriculum with very little leeway, as Sunil was also indicating. Now, why is it not possible, given that we are rethinking the national education policy and so on, to have more flexibility and there to connect with what I said, have more physics-oriented courses available? Now, there are 2 aspects to this. We need to have courses available which can, if need be, given in an online manner, which, for example, teach the basics of quantum mechanics, etc., to a student who's otherwise doing engineering, and bring out the promise of quantum technologies. Whether or not we build a quantum computer in the future that's useful, I think it's pretty clear that in quantum metrology and sensing, as you will know, Arul and others better than me, some of these ideas will surely find important use. A course like that for engineering students, I think, is invaluable. So I think scientists need to have produce that course, but then we need to work with the engineering colleges so they provide the flexibility for students to be able to take it. I think that these 2 need to be done, and I think it's essential to do it so our engineers are positioned for the 21st century, going forward. That's what I would say. All right.
Yeah. Yeah, if I may just add to that, Sandeep, I think that there are a couple of other issues in this thing. One is availability of faculty members, good faculty members in these engineering colleges to actually teach quality physics courses. This is number 1. I think that this may be really the key issue, because we have, in fact, IITs, for example, many of the panelists, some of the panelists here, and there have been many scientists who come out of institutes like IITs, which have a focus on technology, but nevertheless allow students to take a wide variety of courses. And because after all, an undergraduate education is only that, and does not decide the entire future of the student. So I hope that we can address this problem. I think it's a real problem for a fair bit of students in the system. There is a question from Linda Waters on YouTube.
Arul, I personally am having some trouble hearing you. Could you speak up a little bit? Could you speak a little louder?
Oh, I'm sorry.
Yeah, or raise your volume.
Okay, sorry. Okay, so I don't know if this is better. I just shout a little bit. So Linda Waters on YouTube chat says, what do each of you do professionally? I'm just quoting her because I have it in front of me, not paraphrasing this. What do each of you do professionally to include women in physics, particularly at the graduate level? considering that fair treatment by peers in hard sciences in India is already an uphill battle?
Let me just address that. I've been involved for the last few years as, in the American Physical Society. I'm now past president. Last year I was president. And we've devoted an enormous amount of effort to issues of diversity, all kinds of diversity, but gender diversity, which is what you're.
Yeah.
APS has done all sorts of things, has all sorts of programs, Step Up for Women, trying to change the atmosphere, which many women in the United States, for sure, felt physics was not a welcoming environment. In addition to outright sexual harassment and other barriers that are those are easier to deal with, but the cultural atmosphere is a harder one. And convincing women that changing the culture and then convincing women that the culture has changed and that physics is a welcoming place for everyone is not easy. But you might look at some of the APS programs and ideas and copy them or adapt them to India. Some of them have been very successful.
Yeah.
Can I say something if you permit?
Yes.
I think it's a particularly important issue, David. Thank you. I wasn't aware of the APS work, and we will definitely study it. But I think it's a big issue for our PhD programs where the enrollment in STEM areas of women is very low and must be increased. I can tell you what we did in TIFR. We did a study of how women were faring in our entrance exams. We have a two-stage entrance exam, say in physics, a written exam and an interview. And we found that women did much worse than men proportionally in the even first level written exam. Now, what we've started is a summer program. This was the first year, and even though there was COVID, we ran it remotely. So women students joined us from across the country. But we've started a summer program where we get women who are doing their master's degree or last year or bachelor's to come in the summer and spend a month or a little more than that familiarizing themselves with TIFR and so on, perhaps so that if there's a kind of intimidation or something which is at work here, that might help. Because if you look at university exams, and again, some of you will know this better, but this is the statistics I've been told. Men and women do, the women do quite well in the master's and bachelor's programs, but not in the entrance into PhDs, at least in the TIFR system. So there's something systematically at work, but it's very important to address it, I think. And I think with enough research and some amount of, if I can say, nurturing, we should be able to do it. But I think the country as a whole needs to think about this much more. Sorry.
Well, I think we've arrived at the appointed hour. And I'd like to draw this to a close by thanking all of the panel members. This is not easy to have a panel like this spanning the world. It's very late at night here, very early in the morning there, and my internet is going on and off all the time. But I thought this was wonderful. I hope you all enjoyed it. I'm not sure who we're talking to, the audience out there, but I hope you've enjoyed listening to these incredible people and to all sorts of interesting ideas about science, about string theory, about physics, about India. Thank you all. I'm delighted that I could do this. And Rayan, do you want to call this to a close, or Arul?
Yes, I think it will be a good moment to end because we committed not to go beyond 12:30 in our local time. So we should indeed end now. Arul, you agree?
Thank you so much, David, and all the panelists for participating so enthusiastically. I'm really sorry that it's so late there, David, and you also have to address the convocation tomorrow. So yes, so please rest well, and other other panelists. So I want to leave the final words to Ayan. Ayan, please.
Okay, Arul, for conducting this, moderating the question-answer session, and of course, thanks to all the panelists. I think we have created something that is going to stay for posterity, I hope, and it is going to be valuable several years down the line. In fact, one of the journalists has already commented that it is the most informative and enlightening panel discussion she has ever attended. So I guess this opinion will be shared. But at the same time, I should first have to say that our panel has been a bit biased to string theory because it's part of the string theory conference. And we hope to have more diverse conversation and also more diverse panel in the future. But it is just but I'm just very happy that we could be able to honor David Gross and let him share this beautiful conversation that I think is going to be a valuable document in the history of physics, maybe, and at least in the history of IIT Madras or Indian science. So thanks to all of you, and especially, as David said, because of staying such long, and Kumrun, who had to stay up to 2:30 at night, especially, and also to David and Mani, who have stayed awake to very late in the night as such odd hours, and of course to all of you for having your valuable time, taking your valuable time because you have commitments as various administrative commitments, all of you. So, and to take your and Sandeep especially, and then to Shiraz too for this very interesting speech and all of this has been very informative, very beautiful, very simple, very profound, and also very effective. So thank you very much, and goodbye to all of you. Goodbye to all listeners too. Bye.
Goodbye. Bye.
Thank you very much.
Congratulations on your conference, successful conference.
Right. Yeah.
Congrats and thanks a lot.
Bye. Bye. Bye.
Thank you.
Bye.
Thank you.
Bye.